Now invite Manny back to the stage again for an overview of safety issues in MRI, bumps, jumps and burns, static gradient and radio frequency magnetic fields.
Thank you very much. My paranoia that we don't have enough time is increasing as every minute passes. A couple of things. In the break, one of the questions that had been asked of me, I'd like to bring out as a continuation of what we discussed a moment ago in my last presentation and see if perhaps I could get you thinking, or maybe be a little bit controversial. A few people asked me my actual opinion about the different agents. So this is just my opinion. Please do not take this as fact, God Almighty. This is just my guess. If I had to give a guess right now, my personal opinion, as nothing more than that, is that the insoluble bond, in my opinion, in the brain, if I had to guess, I think that that's maybe not a safety issue. And that insoluble gadolinium phosphate, perhaps, I think that causes NSF. Let me say that again, because I'm trying my best to get you angry at me. It's my opinion from now, and it's not based on a whole lot of science, it's just guesswork. I wonder if the dissociated gadolinium that has reattached as an insoluble form to, for example, gadolinium phosphate, I believe in the brain, I actually do think that if I had to put my money down somewhere today, I would guess that that is not a safety issue, and I would think it's biologically, perhaps possibly inert. Sort of like calcification that just shows up in the basal ganglia. And that exact same molecule, gadolinium phosphate, for example, perhaps, I think that same molecule may be exactly what causes, it's a big word, causes. I wonder if that molecule might be the one that causes nephrogenic systemic fibrosis. So make up your mind, Kanal. You think it's inert, or you think it's causing one of the worst diseases that we have no cure for? Yes. Are there any questions? You actually don't know anybody more anal compulsive than I am. You really don't. And I am exceptionally careful about the words that I use. I believe it's inert in the brain. And I believe it causes fibrosis in the body. You see, the brain doesn't heal with fibrosis, does it? The brain heals with gliosis. There's no fibrosis in the brain. It's a special place. And in my gut, I actually am wondering if perhaps that same thing, everyone's worrying about brain retention, and I am too. But if, in fact, some of the linear agents dissociate and maybe form some insoluble forms, I think the body's reaction to that insoluble form in the brain might be inert, maybe. And I'm wondering if that same exact form in your subcutaneous tissue causes an inflammatory reaction that's not stopped and eventually leads to a fibrotic reaction that we call nephrogenic systemic fibrosis. Stick that in your pipe and smoke it. It's just a theory. Does it make it right just because a fast-talking ex-New Yorker is saying it to you? It just goes to show you how little we know, because I think it's an extremely plausible theory. So again, using words like safer and not safer, it would be amusing to me to watch the confidence we have of people using and throwing words around like an abundance of caution, when really you don't have a clue what you're doing, because I sure as heck don't have a clue what I'm doing, and at least I'm trying to admit it and reason my way through it more objectively than simply saying, this looks safer to me. And if you even entertain for a moment that what I just told you might be real, it should fill you with a lot of discomfort of how little we know, because it may very well be that that same agent, which may dissociate and cause NSF in the body, may not be an issue for the brain, but we just want neat packages. But science and medicine, and God help me, biology just doesn't always like to be neat. It does what it wants to do. My job is to try to understand it. Speaking of understanding it, how about if we talk about things I like a lot better, since chemistry makes me break out in hives? So let's talk a little bit about electromagnetic fields. Actually, I don't have the slightest interest in talking about electromagnetic fields. What I do want to talk about is try to take this off without taking off my microphones. This may be a very entertaining next few minutes for you. What is this meeting rated? I actually am not interested in talking about electromagnetic fields. What I am interested in talking about is implants and things that we can do to try to perhaps make a difference in the implants, meaning, can I safely scan them or not? Barbara just said something tremendous. Could you imagine if we had a standardized approach to answering the question? Could you imagine if we had a standardized approach to answering the question, I have some implant, some device, goodness gracious, I have a foreign body from World War II. And you think there's a standardized way to answer the question, can I scan this patient or not? And then you haven't told me what the patient looks like, or how big or small they are, and what magnet, and what field strength, and what orientation, and which coil are you going to use, and what sequence are you going to run, and how are you going to position that patient, and where are you going to center that patient? Are they prone? Are they supine? Are they decube, lateral decube, Superman? And you're going to standardize that approach. Yes, it's already been done. We just have to accept it, that's all. And the way to answer that question, again, going back to aviation, do you have any idea how many different kinds of airplanes there are? Some of them are putt-putt, little tiny piston-powered. You wind up a rubber band and let it go. Some of them have jets. Some of them are turboprops. Some of them have wings that look like this. Some of them are swept back. Some of them are delta wings. Some of them are T-tail. Some of them are straight-tailed. Some of them are inline. Some of them... How are you possibly going to standardize safety? It's been done, right? And there are fine-tuning for each specific situation. So if they can do it, we can do it. We just have to understand, number one, that it's recognizable and that it's accomplishable. And then number two, decide if we want to do it. And if you do, then adopt some standards and then follow them. Really, all kidding aside, that's exactly what Barbara's been trying to do for decades, is to standardize. What's so wrong about that? Imagine if your questions are identical every single time. I told you I give some courses in the US. By the time we're finished, we spend a half a day where you will make up clinical situations for me. Do you understand? You're going to make up. I yell out, by the time we're done, we have a blast. I yell at one person, I point to them, and I say, you, and she says, female, and I say, you, and you say, 37 years old, and I say, you, and you say, brain stimulator left-sided, and you say, it's been there for 12 years, and you tell me. Everyone throws in, so we can randomize the case so that you can see that it's not prospectively fixed. And by the time we're done, we sit there laughing and smiling at some of the things you guys make up. And then when we're done, we say, okay, let me get this straight. I have a neurostimulator, left-sided. It's been there for 3.5 years. We're going to study it on a patient who's a midget and is a male and has a left arm amputation and is going to be done in a GE system using a Siemens head coil. Is that what you want me to do? And when we're all finished, and we ask the exact same questions that they've been asking for the past half a day on that patient as well. The answers may be unique, but the questions and the order is identical. And by the time you're finished, you better be able to answer the question, can you safely scan this patient? Or if there are risks, where exactly are those risks? And are there any things that you can do to decrease them? Now, there's no way we're going to have time to cover 24 hours worth of lectures in the next half an hour. but at least I want to give you a taste of what we need to understand and how you can get towards that process. First of all, I'm about to do a CT scan of you. I'm about to do a chest x-ray. I'm about to do an ultrasound of your liver. When I do that test, and this is our background, this is what we've been doing all these years. If I do a chest x-ray of you, what am I going to do? I'm going to take a flashlight. Okay, it's not visual light. It's x-rays. What difference does it make? It's electromagnetic radiation. I take an electromagnetic radiation flashlight, and I shine this flashlight at my patient. Do you understand? I want to do a chest x-ray. What part of this patient will I irradiate? The left leg. What are you, on drugs? The chest. Okay, fine, don't yell at me. I take the flashlight and I irradiate this patient's chest. I put a receiver on the other side. Some of the x-rays get through, some don't. The more that get through, the blacker it is on the image. The fewer that get through, the whiter it is on that image. I just finished all of X-ray physics. Are there any questions? Do you understand that after it's all said and done, he's serious? What about KV? It's just the energy of the X-ray. MAS, it's how many X-rays did you shine at me? Everything else is fine-tuning. Ladies and gentlemen, I'm finished with X-ray physics. We could talk about the safety and the carcinogenesis, and all. We have to know that, but we're done, aren't we? There are no 40-hour courses on X-ray imaging physics. There's detail that we have to understand, of course, and the math is exquisitely impressive on CT, but it really is the case that some get through and some don't. The more they get through, it's going to be blacker. Wait a minute, what about nuclear medicine? God help us. I'm sorry, is my bias showing? It is no coincidence that nuclear medicine and unclear medicine use the same exact letters. So in nuclear medicine, the X-ray source is in the patient. What's the difference? I'm saying this not to make fun of CT. Goodness gracious, it's MR I'm making fun of. I'm exposing this guy to a chest X-ray. I take a single solitary energy source. I shine it at whatever I want to see, and I get an answer. Do you understand that? What are the risks? I don't know. We're not going to go into CT risks, but listen carefully. Whatever they are, where are they? I'm sorry, I have no idea what you're talking about. Where are the risks of what you just did to that patient? Answer the question. I just did a chest X-ray. Where are the risks? I'm going to guess the chest. Do you understand what I mean by that? That means that 99+% of the time when I'm doing a chest X-ray, what I'm worrying about is radiating the chest, and therefore I'm worried about the thyroid. I would not be worried about necessarily the ankle, if there would be any risks associated with ankle would not be exposed to much of it. Do you understand that? Cool. In fact, it's kind of simple. Let's move on. I take one energy, I expose the area I want to examine, and that's the area that I'm exposing to risk. Move on. I'm going to do an ultrasound of your liver. I saw you in the pub last night. You need an ultrasound of that liver. I take the ultrasound transducer, it's an energy source, and I'm going to shine it at what? His thyroid gland. Don't be crazy, you're going to shine it at his liver. The echogenicity will determine the ultimate image. If it hits an area that's very echogenic, I'll see a lot of signal. If it's going to be hardly echogenic, I'll see nothing. Got it? Any questions? This is so straightforward. Any risks, if any, that I expose this patient to, where did I expose in this body? Where are those risks? Manny, you're scaring me. His liver. Okay, don't yell at me. We never even have to think about it. It's so obvious, even a surgeon understands this. Now, Martin, I want to do an MRI of you. I want to look at your pituitary gland. To do a single MRI of his pituitary gland, I lay him down and I expose his body, essentially, to a strong magnetic field, B0. That's an energy source. It's not enough. I now take a second energy source. It's a second flashlight. Gradient energies, whatever they may mean, I turn it on, turn it off, to reverse it, turn it off. I turn them on, turn it off hundreds, thousands of times per second. And I expose significant percentages of his body to gradient magnetic fields that are doing something anteroposterior, supra-inferior, left to right. I'm not done. And when I'm finished with that, I take a third flashlight, radio frequency oscillating magnetic fields, and I irradiate his body, different parts of his body once again, about this much, to radio frequency oscillating magnetic fields that are changing at millions of times per second, and I modulate that by turning it on and off a few hundred or 1,000 times per second. And when I'm done, I got a 1.5 millimeter thick coronal slice of his pituitary gland. And he's serious, isn't he? It's unbelievable. Ladies and gentlemen, we've never done this before in our lives. I don't have an energy source. I have three to generate every single MR image. Furthermore, it's not that I generate with three different sources. Where I shine those flashlights, where the flashlight's strongest, where are they weakest, has nothing to do with the area you're examining. Listen carefully. The strongest area that you're exposing may be somewhere physically far removed from the pituitary gland you're studying. You think he's making fun. I'm making fun of us. I'm making fun of MRI, not CT, not ultrasound. Those are common sense. This, ladies and gentlemen, is not common sense. It's not common sense that when I expose your pituitary gland, what I actually end up doing, when I'm trying to see an image of her pit, I will take gradient magnetic fields and do this, and this, and this, supra-inferiorly, right? The pituitary gland is the center. Where's the greatest dB/dt? Where's the greatest exposure to a time-varying magnetic field? Where is the greatest strength of that gradient flashlight? Look at my arms. Look at them. Where does the seesaw, where does the teeter-totter move the greatest? Out here. When I expose your pituitary gland, I max out the exposure to your pacemaker, to gradient dB/dt. And I quietly have nothing left to do but go through his pockets. The area you're studying may get the greatest possible energy, or lowest, or anything in between for each of these three different energies. How do you like them apples? In order to understand the risks of MRI, it's almost like you have to understand how to do MRI. In these United States, there are many states in which you don't have to have any qualifications or certifications, and I mean of any kind, to be a radiographer. You don't have to be a radiographer. When the technologist, as we call them, was so angry at his employer in California that he said, at the end of that patient, "That's it, I'm out of here." And he got up and he left. That was the notice he gave. The person who drove that truck got a phone call and was told, "Get in there and scan the patient. Next patient's yours. 100% legal." He said, "How do you turn it on?" "I'll walk you through it. Get in there and scan the patient." It's perfectly legal in many states in the United States. In order to understand safety, you have to understand how we generate images. I have a course I give for 40 hours on MR imaging physics. The next one I give is 2 weeks from now in the United States. It's given to radiologists, radiology fellows, and radiology residents, and technologists. The technologist course is slightly less, but very slightly. Technically, we tell all of the patients that come to our safety course, technically in my house, in-house, my own residence, my house staff, they will have to sit through that one before they can take the safety course. But that's not practical for most places, right? So at some level, we have to at least start with a basic understanding of the imaging physics, which is that it's not one, it's 3 different flashlights. And where you're depositing the energy is going to be critical, because listen carefully, I don't know at all about the UK. In the US, you cannot count on your radiologist to know how to answer that question. In the US, your radiologist may not have a clue. And they may say, it's okay, scan the pit. You're nowhere near this guy's pacemaker. I get questions. I get 50 to 75 questions sent to me by email every day on MR. 3-4 days ago, Thursday of this past week, one of the technologists in the US sent me saying, head of neurosurgery said, scan this patient. Make sure that you're not scanning the known ferromagnetic aneurysm clip. It's an order from a physician licensed to practice medicine. Do you understand? I literally don't know how it works here. In the US, you don't argue with an order from a physician. Your job is to carry out, that's the reason you were hired. And you now have to get up there and say, no. You better know what you're talking about. So to go through the specifics, let's start to show you a little bit about these energies that we've been discussing and see how far we can take it. In looking at the safety of implants, there are 3 areas only right now that I want to focus on, those 3. The static field, static just means non-changing, constant. The gradient magnetic fields, the ones that do this. And the radio frequency magnetic fields, the ones that are megahertz or millions of times per second. Those 3 are the ones that we're going to play off and trade off against safety when it comes to imagining implants and how we can scan them, and can we scan them safely or not. So let's go through this. First of all, we have a tube. For those of you that have open scanners, we'll talk about that more this afternoon. So for the superconducting systems, you have a tube. That tube is the magnet coil. It's a bunch of wires. You put current through them. Faraday's law of induction says you generate a strong magnetic field perpendicular to the motion vector. If you're going in a circle, perpendicular to that is a straight line right through the center. So you generate a magnetic field that looks like this, north-south. Inside that, we have gradient coils, the second flashlight, the second energy source. And after the second flashlight, inside that, we have a third flashlight, and that's the radio frequency coils. There are 3 different energy sources. There are 3 physical different pieces of hardware. Do you understand that? Now, the 0, 0, 0 center point of that one, and that one is the exact same parts of a millimeter in space. They go through tremendous, tremendous effort to make sure that the exact geometric center of the body coil, the RF coil, the magnet coil, and the gradient coils, left, right, antero-posterior, supra-inferior, all of those center to the same parts of a millimeter in space. But there are 3 different pieces of hardware, and they each do unrelated things with 3 different energies, listen carefully, and each have their own risks. And they're each being deposited in different distributions over the human that you're about to place in there. Let's call it your patient. And so different parts of your human will be exposed to energy source flashlight A compared to B compared to C at different strengths and different relative risks in different parts of their body. So if right now there's a tube inside all 3 of them, and you choose to put your patient in there, that star is meant to represent some implant at L4. I don't know what example to use here. This is my first trip to Scotland. A, I'm in love. B, not with your weather. B, actually it was magnificent here over the weekend. B, I hope you guys ask so many questions this afternoon. And you think it's because I really love when you want to learn. No, I just want to hear your accent. I just love it so much. I could listen to you talk for hours. I was out there with Barbara a few days ago. I just sitting there like, yes, what else would you like to say? She said, Manny, I asked you a question. Yes, I know, just keep on going. This thing at L4, in the US, I'd say it's a bullet fragment. You guys, a bullet is sometimes people shoot each other in the US only. And sometimes it leaves, anyway. So this is some kind of a foreign body or an implant of some sort inside, let's call it L4 approximately. And so now energize, whoops, that's not energize. Turn it back on. Now, we're going to energize the gradient coil. The magnet coil, the red one, is always on. So now we're going to energize the gradient coil, and we energize the radio frequency coil. That means turn the flashlights on. So now these energies are being irradiated. The red, we'll get to a lot more specifics in a little bit, but the red has a spatial distribution for its energy that is more or less homogeneous to what's inside, and we're going to see how erroneous that assumption is in an hour or so. The green has its distribution, and the blue has its distribution. And again, we'll see how extremely inaccurate this homogeneous potential really is in just a few minutes. But you can see now that that implant, that device, that foreign body at L4 is being exposed to 3 different energies. Does that make sense? And so whatever risk is associated, if any, with flashlight A and flashlight B and flashlight C would need to be assessed before I could answer the question, Manny, can I safely scan this patient with this implant? Does that make sense? The same exact patient, if you want to, I can say, let's do a head instead of the T-spine. And so now that I'm doing the head, maybe I'll take a different flashlight for green. Instead of using a body coil, for lack of a better name, to radio frequency irradiate this patient for one of those 3 energies, let's take the flashlight out. We don't take it out, we just turn it off, but conceptually, and take another flashlight which will irradiate the head only, and let's turn that one on instead. Does everyone understand that? I just am using a different piece of hardware. And if I irradiate that now, do you understand that the relative risk, because of the exposures to these 3 flashlights are different, the risk is now red, based on what I've taught you so far, red may not have changed, or has it come back afterwards? Blue is entirely different. Green is entirely different, obviously. So now, what does your doc say? Hey, can I safely scan Scott with this implant with MR? And you already start to see how the question is scary. It shows a lack of understanding. You may be able to scan Scott in MR for study A, but not study B. Depending on what part of the body are you irradiating with which energies. It doesn't apply to CT. It's a one-trick pony with one energy source. The question doesn't apply to nuclear medicine. It doesn't apply to ultrasound. It doesn't apply to PET. Ladies and gentlemen, it doesn't apply to anything you have ever seen before in your lives we have ever used in diagnostic imaging of humanity. This is the first time we're using 3 different energy sources to generate one single image. And so you and I, for goodness sakes, if we don't understand that, who's going to? The neurosurgeon? They can barely spell MRI. It's your job to understand that distribution. And so the question, can I scan them? Almost always going to have to start off with a, it depends. What are we looking for? Tell me again, start from scratch. So one of the first things to understand in MRI is that you have to stop the clock and get more information. She's pregnant. No worries. I can shield, or I'm going to scan an ankle. I'm doing a head. Technically, I don't really need to shield. When you do shielding in CT for a head study, all the physicists tell us it's really for you. It's for the patient's psyche. The scatter to the fetus is essentially 0 Do you understand? So where are you irradiating tells you where the risks are. So at least, ladies and gentlemen, we need to know where are we irradiating. That's number one. Number two, multiple flashlights. We may be irradiating that implant or foreign body with this flashlight, but not with that one. If I put them in this position, it may max out this flashlight, but minimize that one, etc. So now let's talk about these for a moment. Static magnetic fields, the non-changing, static, constant magnetic fields. You have a 3 Tesla, a half Tesla, a 1.5, whatever your machine is. The static magnetic fields, there are lists and lists and lists. I used to put these together just for education and entertainment values of the things that people have been exposed to and have inadvertently, and in some cases intentionally brought into MR scanners. And in the breaks in between, come ask me about the acetylene torch and the steel-tip shoes. But the key about these is that the number, and please don't think I'm trying to be all-encompassing, the most important factors here for static fields is that the static field will cause rotational and or attractive forces that all of us are aware of. And we are pretty familiar with the fact that wrenches will tend to align, rotate to a magnetic field. That if you bring that wrench into an MR scanner, it will tend to fly into the MR scanner. We're going to spend a little bit more to discuss that in a tiny bit more detail, but luckily for us, those are pretty much kind of intuitive already. Not so fast, but they're at least a good start. And of course, another safety issue is that you may have, your patient may have on or in them some device, forget the fact that it could move for a moment, some device may be on or in your patient upon which they may be dependent. Of course, people use examples like pacemakers, defibrillators, but it could be multiple devices that the adequate function of that insulin pump is an integral part of the safety of this question of can I safely expose them? You don't want that insulin pump suddenly malfunctioning and delivering the entire reservoir of insulin to the patient as a result of the MR scanner and having them comatose or dead. And yes, these have occurred multiple times in MRI. So the idea of safety not just being mechanical from things flying or moving, but also things that you may not be suspecting the patient may be dependent upon, we have to make sure that those devices still work. It's not just they may be dependent upon. Somebody brought into me for testing, we have a fire extinguisher. And it says on the side MR conditionally safe, and it's been tested for MRI, and you can bring it in. It's aluminum. It's not going to go flying into the scanner or anything like that. We tested oxygen systems. Oxygen delivery systems means not just the tank, but the tank, the stem, and the regulator. Right? To put the three together, you have an oxygen delivery system. And it says MR conditionally safe. And we're testing them. And then one position is fantastic. It is exactly what it's supposed to. And you measure it, and I'm doing testing, and it says 6 liters O2. And yes, indeed, when you measure, 6 liters of O2 per minute are being delivered. And you reposition the oxygen tank perpendicularly. And the oxygen flow goes to 0. It says 6. Just like my last car said 120 miles per hour, but it ain't gonna do 120 miles an hour. You understand that? It says 0. There's 0 flow in this position. But it says conditionally safe. There's a ferromagnetic tiny little spring in the regulator that under certain conditions is going to compress. Next thing you know, you have no flow. You think it's doing everything you expect it to do. That's what I mean by safety of a device upon which the patient may be dependent during or subsequent to that MR exposure. Got it? That's another aspect of safety relative to static magnetic fields. For your entertainment, I've taken some slides together to show you things that have found their way into MR scanners, but the truth is, and we look at them and you laugh or you say, holy cow, or you gasp, but the fact is that they do serve a purpose. Because when you see them, you're going to be worried that Manny is going to take your incident next time and stick it up there, and you don't want to be on his list of hit parade. In the United States, there was an epidemic of buffing machines. I wanted to call the Center for Disease Control and say there's an outbreak, an epidemic of This is a buffing machine. Buffing, that used to be a head coil. Buffing machine, 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 buffing, 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 buffing. Those are all, I mean, you don't understand. Why do these things keep happening? We'll get there. Physicist brought this bucket by to assist the maintenance person. I like to say garbage in, garbage out, but in this case it's just garbage in. It's a trolley. This is actually a gun. It shoots things. The date is interesting because it's just a few months ago. This guy shot himself through his legs and was arrested for reckless endangerment. He brought the gun into the MR scanner after saying he didn't have a gun on him, and it went off as he approached the MR scanner. Passed through his thigh and the other thigh as well. In Brazil, somebody brought a gun in and it fired and killed his iPhone. If you're interested, come up in the break and I'll show you pictures of a dead iPhone with a bullet right through the middle of it. It was a perfect shot. This is an IV pole, one of those adjustable patient pop beds. This is the bed. This is the rest of the bed. Bed, stretcher, ICU bed. This is a crash cart. Gives a whole new meaning to the term. EKG machine. So, ladies and gentlemen, where you take a wrench in, you let go, it flies to your magnet, right? Where is that force the greatest? Where is that force the greatest? Total. How much time do we have?
Half an hour.
Thank you. Where's the force the greatest? Where in that room is the force pulling this wrench into that magnet the greatest? Is it greatest at the control station? Is it greatest in the center? Is it greatest in the, where physically, three-dimensionally, is this attractive force going to max out? Isn't that a reasonable question? And if you don't know, who's going to answer that? So the force is greatest for almost all of these superconducting systems, the Bohr systems. You know how you put your hand on the side and you reach and you say, "How you doing in there?" See my hand? Bingo. That's about where it is. It's sort of right, it's actually just inside the opening for most scanners. I'll show you in a few minutes. It's sort of just inside the opening, right up against the outside. But the force changes everywhere in the room. Now, a 3 Tesla if this entire room was exactly 3 Tesla, north and south, got it? So I take this iron wrench, I line it up so that it's north-south. Everybody with me? And this whole room is exactly 3 Tesla, homogeneous as can possibly be. If I took this right here and I let go, got out of the way, and let go, what happens? Talk to me. It will go, it would, it would remain aligned with the field. It wouldn't move. It would fall. Did you hear what he said? It would fall under gravity. No, it would. Do you hear what he's saying? You let go of this. Why doesn't it? It would remain aligned. It wouldn't turn. And it would fall. I don't understand. Why wouldn't it go that way or this way? Or so one of the most important things he's teaching you, this is so strange. Magnetic fields don't attract metal. We'll get to what does attract it, and yes, it is sort of magnetic fields. That 3 Tesla is not attracting it. When you're walking to an MR scanner, if I take the same exact wrench and let go, phew, it flies in. Why does it fly in? But if you're in it, it doesn't go flying anywhere. If there's gravity, it'll just fall down. Because what attracts it is not the field. It's the difference in the field. Thank you, it was perfect. What attracts it isn't the field 3 Tesla, 1 Tesla. What attracts it to go that way is that if I'm walking into the MR scanner room, and over here there's a certain field, and over here the field is less, it will translate, it will move, it will feel a displacement force in the direction of the greater field. If everything here is completely homogeneous, there is 0 difference across the wrench from here to here, and so there's no displacement force, that way, this way, that way. Oh, there's gravity, so then it'll respond to that force. But from a magnetic point of view, there's no translational force because there's 0 delta, there's 0 difference across it. So the first thing to recognize is that there's a dBdx. What does that mean? A dB, a d we use as derivative. Don't get bent out of shape. It just means a changing magnetic field across a changing position in space, x or z. dBdx or dBdz means a different field from here to here. If you take a centimeter, what is the strength of the magnetic field here compared to the other side of that centimeter? If it's non-zero, you have a dBdx. And that's given a name, a magnetic spatial gradient. Some people call it a static field gradient. Don't get confused. We'll get to the imaging gradients in a minute. This is not the imaging gradients. And that just means if I put a magnet on a bar magnet on that table, as I get closer to it, I'm getting exposed to a stronger, 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 stronger magnetic field. That's all it means, right? Here it's weaker, it's stronger here, it's stronger here. You could, listen carefully, I could map out, I could generate a plot of the magnetic field here, 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 and therefore the difference. For every centimeter here, it's a half a Gauss stronger. As I get closer, for every centimeter I get closer here, in that 1 centimeter, it's 3 Gauss stronger. Does everybody understand that? So you could measure 2 different things. Think with me, stay with me. I could take this whole room, put a very strong magnet here, and I could generate plots around it that shows the strength of the magnetic field. Here is X, here it's Y, here it's Z. Do you understand? Just what is the strength, what is the strength, what is the strength? I could take that same exact plot and now modify it and show the difference between the field here and here is X Gauss per centimeter. The difference, the magnetic spatial gradient. Oh, over here, it's even bigger. Over here, my gosh, it's even stronger. The difference is much more substantial here than here. You're right up against this bar magnet. Oh my gosh, now it's unbelievably strong. In just 1 little centimeter, you can go up 1100 Gauss. Does everyone understand that? So now you need to think of 2 different things. Every static field generates 2, in a sense, energies, flashlights. It generates a static field plot, a distribution of spatial energies. Stop. Imagine this. We turn all the lights off. I take a flashlight out. I go to the back and I shine it in the front. And I say to you, ladies and gentlemen, draw out a plot for me, a 3-dimensional plot, a spatial distribution energy plot of the energy that I'm now irradiating this room with. All of you could easily picture a widening cone of greatest energy is by far right up against the front of that flashlight. Does that make sense? Right there, it's strongest. The further away you get, inverse square law, remember that? The further away you get, it gets weaker, 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 but it stays pretty much, I've got one of these modern flashlights that you can sort of focus, and so it's a cone that reaches about that big by the time you get to the front of the classroom. Now, what about the back of the room? You really think I'm not irradiating the back of the room? How could you be? You're doing this. Because it bounces all over. Scatter. Remember electromagnetic radiation? The guy in the back of the room might even be able to vaguely see the shape of a paper or a book or something because it's scattered. So there's very little background radiation that it produces, but certainly most of it is in this cone, and it's a lot weaker there than it is here. Do you see what you just did? You put together in your mind a 3-dimensional energy distribution for that one energy. And that's what you have to do when you speak to the neurosurgeon. Not to him or her. That's for you. It's for you. You have to be able to generate your own plot. We'll do it together this afternoon. You have to generate your own spatial distribution plot. When you shine that flashlight, that magnetic flashlight, in this part of that magnet, it's strongest. Not the center. Out here, what's strongest? There's 2 different plots, the strength of the field and the magnetic spatial gradient. What attracts in certain types of metal called a magnetically saturated metal. What attracts magnetically saturated metal to a scanner is not the field strength. It's independent of the strength of the field. What attracts it is the difference. The greater the difference across that wrench, the stronger the force to displace it in that direction. Do you understand? dBdx, magnetic spatial gradient. Now, certain metals, could you imagine if I took this iron and I stuck it into a magnetic field and held it so it's not going to move? As you expose it to a magnetic field, it obviously is going to magnetize it. You guys are okay with that, right? Could you imagine that if I expose it to an even stronger magnetic field, it's going to get even more magnetized? You need to accept on faith that there is a magnetization level that this can reach, that beyond which I could quintuple the strength of the magnetic field to which I expose this to. It ain't going to get any more magnetized. It's maxed out. Got it? You can never magnetize this iron beyond that number. That's the strongest it could ever become magnetized. We call that magnetically saturated. For metals that are magnetically saturated, the only thing that determines the force of displacement that's going to fly into that magnet, the only thing that determines that is magnetic spatial gradient, dB dz. If this whole room is 1 Tesla, it ain't going anywhere but down because of gravity, because there's no dB dz, it's 0. Now, if this is not fully magnetized, it's magnetically not yet saturated, then the displacement force, they call it a force product, and it's the dB dx times the B0, the strength of the static field. Fine, congratulations. But in either case, you need to understand it's where is that difference the greatest that's going to be the main player for us. Let's move on. The difference is greatest right about here. Where in that room is the dB dx least? Weakest, and therefore displacement goes to 0. Well, for example, where in that room is it weakest? Outside the room. That's a dumb answer. Yeah, but in the bathroom down the hall, there's no dB dx anymore that you can measure or care about. And where else? So far from the magnet, of course, and where else? Talk to me. In the exact, we just said, if the whole thing is 3 Tesla, well, the center is 3 Tesla. You pay fantastic amounts of money to have these manufacturers warrant for us that it's exactly 1.5 or 3 within X number of parts per million. Your written warranty tells you how unbelievably homogeneous it is in the center, about the size of a basketball, 30 centimeter diameter spherical volume. So in the center, ladies and gentlemen, displacement goes to 0. You bring that wrench somehow, not that I'm advising you to do this, but if you had the wrench in the center of the magnet and let go, I guarantee you come to the course, I'll show you, it drops to the floor. It doesn't even know there's a magnetic field around. So the pacemaker in the center of that scanner is going to act differently than that same pacemaker when you're doing their lumbar spine. Do you understand that? For those of you, if there are any cardiologists here, or those of you with that background, it will switch to asynchronous mode if you're doing his lumbar spine. And it will go back to auto-pacing and detecting and everything else if you didn't take care of it beforehand. In the center, it won't even know you're in a magnet. And it will sense, and it'll be doing everything else if you didn't program it prospectively. I don't care how many Hall switches are there. Nobody cares. It won't detect it. And if you're scanning and you're inducing, because of the other flashlights you're using, you're inducing pulses that are detected by the pacemaker, it will see those pulses, it will think the patient's heart is pumping, and it will deliver nothing. And watch him die, thinking all along this patient's just fine. Take home is just in the center versus not in the center. There are different energies. Static field that this pacemaker or device is exposed to. You go into the MR scanner. The patient has some kind of ferromagnetic something. You didn't know. It happens to the best of us. You start the scan. Oh, my God, there's a huge artifact. In the center of the scanner, there's no translational force. Where are you going to get into trouble from translation? When you try to pull them out. That's when they go through dBdx. Do you understand? Maximum. Where is it greatest? Torque differs from translation. Torque, he said, do you remember the first thing he answered was, it will still stay lined up, but it'll fall. Lined up is torque. And lined up is the simpler one. The strength that it's going to make it want to do this. If it's a sphere, it has no preferential orientation. But if there's an asymmetric axis, if it's anisotropic in its shape, then the long axis is going to, they always try to say, it will traverse the fewest lines of force. You know those diagrams they show of a bar magnet with lines going around? So take that piece of metal, if it has a long axis, it will try, it's not going to cross those lines of force going this way, it's going to try to line up parallel to them, wherever it is. So if it's in the field, it'll line up north-south. And the stronger the field, the more it lines up, the greater the strength, to keep it that way. You try to turn it, it'll flip back with greater strength, the stronger the field. So wherever the field is strongest, torque is strongest. Where is field strongest? Almost all of us have been trained, and appropriately, to answer the center of the, that's your 3 Tesla, right? The center of the bore. So in the center of the bore, B0 is strongest, and dBdx is 0. This is such a sick field. In the center of the bore, essentially, you max out torque, and you have 0 translation. On your way out, translation is going to increase and peak, and then decrease. Whereas torque just gets weaker and weaker the further out you go. So torque is maximum at the center, and I'll show you exceptions. And where is it minimum? Far away. Further away you go, the less the B0, therefore the weaker it is. Translation is really dependent upon more, so at least at this stage of your education, it's mostly dBdx. And dBdx is greatest for the superconducting systems. It's sort of at the entrance. And so it's translation. Where is it minimized? The center of the magnet, or far away. Maximum for translation is just inside the entry, at the periphery, not in the center. If this is the bore, it's not here. If the bore goes from here to here, it's not here. It's up against the side, the edges. Even 3-dimensionally, out here, it's noticeably, markedly stronger than in the center, even if you're standing at the front of the bore. This is a plot of the static field. 3 Gauss, 5 Gauss, 10 Gauss, et cetera, et cetera, et cetera. And this is the MR scanner. The patient goes in this way. Everybody see it? But it's a 3-dimensional static field. This is a plot of the magnetic spatial gradient. Remember we talked about, people use the term dBdx or dBdz or static field gradient. They all mean the same thing. And this is the difference in field from place to place. If you have a long bore, the greatest is going to be right about over there. If you have a short bore system, it's going to be in approximately the same location, but notice that it's going to have different strengths. One of the manufacturers presents their spatial gradient as the Gauss per centimeter. Others might report it at Tesla per meter. And again, it's just showing you a diff. This is the bore, and the patient would come in this way. If this is the bore 1.5 and 3, this is showing you where the dBdx is in Gauss per centimeter, and here it's 140, 250, 300, here it's 800. And this one for a 3 Tesla, it goes to, here's 1,000, 1,200, do you understand? But again, where is it greatest? About here, where you put your hands on. Different manufacturer. The red shows where it's greatest. Side view, spatial gradient. Sometimes they present it to you with text, which I can't stand, but they do. Another manufacturer is presenting, here's a side view. This is the B0 plot, the strength of the field here, or here, or here, right? So you see half Tesla, 1 Tesla, 1.5, 2, 3. Now watch this. This is the spatial gradient. Got it? So the spatial gradient, it's 0.3 Tesla per meter, 0.5, 1 Tesla per meter, 3 Tesla per, do you understand? So it's, and again, the strongest is where the X is. And then some of them, and only some of the manufacturers, provide you with a force product. For unsaturated metals, where's the greatest attraction? And that's going to be in the same approximate region as well. Looking down the bore for yet another MR scanner, I'm trying to remind you it's a three-dimensional field, which means that as you look down the bore, in the dead center of that magnet, the field strength and the dBdx is noticeably different than as you get further and further out radially towards the walls. Does that make sense? Of course, you're standing next to the flashlight, the hardware. And so out here, they give you these numbers for the different diameters. So I just took this table from that company and this picture from that company, and I put them both on the same page to have you understand this is what they're talking about. So as you can see, there are different strengths in different positions radially, not just as you enter the MR scanner, but even from the center of that patient to the skin. Using one example, implants, devices can be labeled. So now, look at me before you look back there. Now you understand why when it comes to labeling implants for MRI safety, you have 3 flashlights. You have 3 different energies. One of those energies, static field, is going to break down into 2, the strength of the field and the magnetic spatial gradient. So now you understand why when they try on these labels for all of our regulatory agencies internationally, when they label, can I take this Blorg Model 300 into an MR scanner? They have to give you thresholds of safety for all flashlights. And so they will list 4 different things at least. They will list, well, for this flashlight called B0, it's safe up to 1.5 Tesla, or 3 Tesla, or a half Tesla. Do you understand? Then, when it comes to dBdx, we will accept this up to 720 Gauss per centimeter. Do you understand that one? Because in a sense, it's 2 different flashlights. Torque, translation. And so the device will have labels, static field 1.5, static gradient 450 Gauss per centimeter at 1.5. When they tested at 3 Tesla, they tested at 720. Do you understand? It's different thresholds, but now you know why. They will also report, as you'll see, other safety thresholds we're about to cover. So when it comes to flashlight number 1, the static field, it will break down into static field and static field gradient. Both of those will have limits, maxima, that you have to deal with. Let's move on. Thermal effects. Radio frequency energies. There are multiple potential risks from this flashlight called RF. The only one that we're going to deal with today, and the only one that from a real world basis has clinical consequence for us day to day and all of our patients, is thermal. Radio, if I take a magnetic field, and I take a bar magnet, just a regular bar magnet, north-south, and I hold it in front of you, that's a static field. If I do this, or better yet, excuse me, if I do this, she now is experiencing a magnetic field that's getting stronger and weaker. Does everyone see that? Stronger, weaker, and it's oscillating. If I could do this at millions of times per second, which is exactly what we do in MRI, where if the field is this way, perpendicular to the static field, we take another magnet and we oscillate it at millions of times per second. Resonance can occur, we can get images. However, in order to do that, I had to irradiate her with a second energy source. We'll call this the transmitted radio frequency energies, the RF source. Got it? you will hear people referring to the RF energy as B1. If B0 is a static magnetic field, 3 Tesla, half Tesla, 7 Tesla, B1, in all of our articles, B1 is the oscillating magnetic field. Are you with me? It's a different flashlight entirely. Do you understand? It's completely physically different. What we irradiate, how we irradiate, what is exposed to this one versus B0, it's unrelated. If I expose you to an oscillating magnetic field, that can relatively efficiently, indirectly, result in heating that patient. This is the most common adverse event in MRI. The most common event, that's reported to the regulatory agencies, especially in the US, but I think everywhere, is heating, is thermal issues, is burns. You spend 5 hours on that in the course. You spend 4 hours on static field. We can quantify how much energy that I am transmitting an oscillating magnetic field. We can quantify how much your body, you, the patient, will absorb. We stink at that. Ladies and gentlemen, we are poor as an industry, and everyone agrees to this. There's no controversy here. As an industry, we are poor in attempting to accurately quantify how much is my patient going to absorb. I took this flashlight, I shined it from the back of the room to the front. How much did you absorb? Did you hear what the question is? I didn't ask you how much is it. I asked how much did she absorb of that. We're not too good at that. We're not too good at that. But it's the industry standard, and we call that SAR. Specific, listen to the word, absorption rate. And that's attempting to have the goal to suggest that I can quantify the rate at which you're absorbing energy, the rate at which your body is going to soak that energy in. And that's the SAR that's reported. And we have limits. This implant can be exposed to this specific absorption rate for that amount of time. Does that make sense? Because we're trying to limit heating. You will find that more recently, the manufacturers are being encouraged to switch, and some of them already have, and you'll see in a minute, you yourselves are using some that have changed, where instead of trying to say, what is the specific absorption rate? What is it that your patient is calculated, theorized to absorb of the energy you're about to transmit for the study you're about to do on his pituitary gland? How much energy will his body absorb? That would be SAR. And we attempt to do such predictions. And the different manufacturers use different equations to calculate that. And do you know what the equations are? Do you want me to tell you what the equation is? None of your business. No. He's serious. It's proprietary. Let me say that differently. It's a secret, and you have not been invited in. This is serious. It's a secret. They do not reveal it. And they are different, and they've been very kind. I have non-disclosure agreements. I've seen their equations. I know how they do it. They're not the same as each other. They have different results. You take the same patient, I stick you into this magnet versus that one, I'm going to get different numbers. And it's proprietary, and they all stink. Some manufacturers are more aggressive. They want to be able to deposit more energy. I can do the study faster. I can compete with a competitor faster. Well, it may be a little bit less safe. We can live with that. Others say, no, my attorneys run this company, and we're going to be very, very conservative. And it shows literally in the equations that they use. Others now have said, wait a minute. We stink at being able to quantify how much you're going to absorb, but you know what we can do a better job of? I can tell you with frightening levels of accuracy what I'm going to shine at you. Now that I know rocks. I have this flashlight. I'm going to stand at the back of the room. I'm going to shine it there. I can tell you exactly what power. I'm going to tell you the wattage to the 10th decimal plate. I know what I'm going to put out. Do you understand the difference? One of them is, what am I putting out? One of them is, what is my patient, I think, going to absorb? What are you going to transmit? That we're extremely reliable. That would be B1 RMS. B1, you remember that? Magnetic field that's oscillating. B1 root means square. So you now may see on some, watch, don't look at me, look at yourselves. Raise your hand if you work on at least one MR scanner that reports not only SAR, but now you have in your own practice seen B1 RMS being reported on your MR scanner. Raise your hand and everybody look around, see around you what you see. So there you go. This is, even for the US, it's about a little bit more, not much. You had maybe 5% of you here. In the US, it's maybe 15, 20% of the sites already have B1 RMS being reported. But it's a switch that is being strongly encouraged by everyone. This is the most confusing of the three energies because B1 RMS is not going to hurt you. The B1 doesn't cause the burn. The oscillating magnetic field, to the best of our knowledge right now, not talking biologic, but we're talking about thermal, is not going to heat you up. What will heat you up and cause injury, potentially a burn, is that an oscillating magnetic field can induce an oscillating electrical field. We've learned that the word itself, electromagnetism, shows you they're intricately intertwined. And Faraday taught us forever ago, if you have a changing magnetic field, it induces an electrical field perpendicular to it. You have a changing electrical field, it induces them. You can't separate them. And so if you have an oscillating magnetic field that I irradiate your body with, this field induces that oscillating current in your body, because your body is an electrical conductor. And those electrical currents that I induce, the E fields I induce in the patient, or would you be happier if I said in the lead, in the implant, in the device? Those are the bad guy in this movie. It's the E fields that cause the burns. I can predict exactly where I'm going to deposit the B1. If you take appropriate trained background scientists, physicists, and give them the appropriate software, they do an impressive job, if you let it run overnight, yada, yada, of modeling. You can predict with certain levels of accuracy, if I irradiate you with this radio frequency oscillating field shaped three-dimensionally like this, in your body I expect the following currents, electrical fields, to be induced. We can do a pretty good job of that. The first pacemaker that received FDA conditional safety approval, in order to receive labeling that said you are MR conditionally safe for the first time, Medtronic had to go through simulations. Of course, and also had to do real experiments with dogs, humans. They had to actually do it, but they modeled. They modeled the pacemaker that they were trying to get approved and the leads in 22 human forms. Tall, short, male, female, fat, skinny, 22 human morphs. Over 1 million total possible tracks. Was it a left-sided pacemaker with a left-sided lead, right-sided lead? What was the length? What was it? Was it coiled? Was it not coiled? 1 million different possible configurations. And then they took a few hundred of those and they reproduced them in labs to show that it could be a good predictor. And on the basis of that, they got FDA-approved labeling. We can do a pretty good job, given enough time and money, at predicting the E fields, but it's unbelievably complicated and complex. So instead, we expect you to do it in your head. No, he's serious. Instead, it's not the B field. I'm going to irradiate you from here to here. I'm going to irradiate her head. I'm going to irradiate her T-spine. Do you understand? I know what I will irradiate, but irradiate is B1. But the B1 doesn't cause the injury. What causes the injury? The E fields induced by this oscillating B1, right? You have to know where those induced fields are going to go. And where are they going to go? We're not going to be able to cover that in detail in this course. But I'll give you a hint. In order to understand that, you have to think like an electron. I want to have a shirt made up. Think like an electron. See if anybody gets it. The universe. Here comes Manny's philosophy of life. Based on an entire life of being exposed to science, I've come to the conclusion that the universe, please forgive me, is frighteningly male. what defines every chemical reaction, every electrical interplay, everything that happens in the universe? Path of least resistance. The universe is a guy on a couch with a beer, lying down, looking for the remote. Everything is going to be path of least resistance. Everything. It's unbelievable. We're going to take a break and come back in a minute, but before we do, I want you to picture what I'm saying. If you were an electron, where would you go? That's what you have to think of yourself. You're lying there minding your own business, and something is going to push you on the shoulder. Stay with me. I know this sounds childish. I guarantee you, I promise you, I'm not talking down to you. I'm a kid. I'm a kid. I'm just sharing with you how I think of things. You're going to get pushed. A force is going to materialize. You're an electron. A B1 is going to suddenly show up out of nowhere, and out of nowhere, by Faraday's law of induction, is going to shove you. Where are you going to go? You can go anywhere you want. Where are you going to go? Look around you. You're not going to go through that wall. You're going to take that hole right there. Just as I'm 100% certain that practically in real life, could you scale that thing and throw a rope and climb? It's possible. Mathematically and statistically, it's not going to happen. You will file out that door. And when I irradiate your head and your C-spine, I know where that electron's going to go. It's going to try to form a loop. And it'll always, 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 always follow the path of least resistance. Which means that if I'm lying in the anatomic, also known as dork position, and I irradiate from here to here, I have this RF coil, and I start transmitting. And I'm going to induce electrical voltages, and I'm irradiating from here to the top of my head. I will cause electrons to go and say, "Ooh, what's this?" and go right down my arm. Leave the volume of irradiation. Come back to my leg and come up here. Because I see a nice, large, easy-to-follow loop right there. And if there's a high resistive part of that loop, an area of that loop that offers high resistance to the flow of that electron, like right here, that's where there'll be the greatest generated heat, and they're going to get a burn right there. And I did an MRI examination of their neck. When you come back from your break, I'm going to try to make some sense out of what I just said to you.